Okay, doing a quick little video on these reaction coordinate diagrams. Now, the picture I have here is right out of our textbook, and it shows the reaction coordinate diagram for the reaction of 2-butene with HBr going on to 2-bromobutane. And it shows the intermediate steps where we're creating the carbocation, and it shows that there are transition states. So this is the type of mechanism or diagram that we get if there's a two-step reaction. Now, there's a lot going in on this to come up with this diagram, and I figured the best way to show what this is doing is to actually recreate it. But I'm actually going to do something that's slightly more complex and has more than one blue line. Well, this is a blue line. It's going to have two of these because I'm going to do something that ends up with two different products. All right, so which one we're going to look at? We're just actually taking that 2-butene and adding a methyl to it. Now, before I actually do the reaction coordinate diagram, I was going to do the full mechanism so we can see what is going on. And at least at first, I'm going to do the mechanism for just the major product. So I'm going to start by having that nucleophilic double bond come over here and attach the hydrogen. And if I drawn that with a double bond, we'd have it going on here. All right, so Markovnikov tells us that we're going to put the H on the side with more H's for the major product. And then our second reaction, we're going to have this come in and attack there to get our final product. And I'm going to write this down here. Now, before I actually do the reaction coordinate diagram, we're going to go ahead and take notice that this thing, even though this is the major product, since that second carbocation that we could have formed is secondary, it could still form. So we're going to show the reaction, still the same attack, and still the same thing happens. But instead of forming the carbocation with the charge on that location, we're going to add the H there. And then the other CH becomes the carbocation. Still Br floating around. Bromine still attacks the carbocation in the second step, but the second step we end up with a different product. All right, now, being that this is just an addition, we know that this is the major product, but the reaction coordinate diagram can actually help us see why when we actually figure this all out. So we are going to do the reaction coordinate diagram at first just for this first reaction, the one that forms a major product, and then we will add this to it. So I am going to do this on this page. So got our Cartesian coordinates, and I'm going to start at a low energy with the, and I'm going to do just the carbons with the 2-methyl 2-butene and HBr. And we know the first intermediate line, or the first thing that we're going to, is this first step. So we're going to have a huge amount of activation energy, which is involving getting this H attached to that, and we're going to form this carbocation. And since a carbocation has a carbon with only 3 things on it, we know that's going to be incredibly unstable. So that's going to be very high up in energy. So we're going to go way up through a huge amount of activation energy and come down just a little bit to our first intermediate, which is that more stable one. Now, the second step is just that bromine going on there. So lots lower activation energy because there is going to be a strong attraction there. Only thing that's going to slow it down at all is the bromine has to get around all those other carbons and hydrogens and such. So some of the electrostatic interference will slow it, but for the most part, it's going to be an easy step. So we're expecting a relatively small hill, and then we go down. Now, how far we go down is based on what our product is, and we will find that, I am making everything go away. We are going to find that for the most part, everything that we create by adding to an alkene is more stable than the alkene, and that's no exception here. That haloalkane that's formed is lower in energy. And the one that we formed here, I'm going to draw that C up there so we can see it. It's bromine. All right, now, the things that we actually see on a reaction coordinate diagram is we see a huge amount of, and I'll change ink here so we can label this. This increase that goes from the starting point to that top is your activation energy. The difference between our starting product and the final product is the delta G, or the Gibbs energy. Tells us if it's exergonic or endergonic. Basically tells if it's favorable or not. And the highest point is our slow step, and this one is what we'd see when creating a carbocation is always hard, so it's going to be your slow step. All right, now, technically, we have a competing reaction, and that's this second one. Now, we know from our textbook that a secondary carbocation is not nearly as stable as a tertiary, and we actually see that. It would be slightly higher in energy, and it would require slightly more energy to separate it, so it's going to be a higher hill. And I'm still going to start at the same part. Now, the second hill is just a little hump, just like before. And the final product is not nearly as stable. We'll find that the halogens being on a tertiary location make for more stable, slightly more stable than on a secondary position. And that is why we end up seeing the red line more often. It requires less energy to get over that first hill because it's a more stable carbocation. Therefore, we get more of that final product. All right, let me know if that helps.